In this project, we attempt to prove the principles of conservation of energy by calculating the energy before and after a crossbow is fired. To do this, we needed to make a few assumptions. The first is that the system was frictionless, and this should be an okay assumption since we are using bearings under load and the steel ball we are attempting is able to freely roll. Another assumption we are making is that the ball is small enough to treat as a particle. This should also work because the mass is small relative to the rest of the apparatus. Lastly, we also assumed that our springs complied with Hooke's law. This is likely our biggest assumption, as real springs rarely comply with Hooke's law, as it was designed for rigid bodies, not springs.
The first thing we needed to do to accomplish this task was to determine the spring constant for our springs. Since we didn't buy them from an engineering supplier, the value was not listed on the website, so we had to find this ourselves before beginning testing. To do this, we took objects of known mass, attached them to the end of the spring, and plotted the change in length with respect to weight. We then took the line of best fit across the data. The slope of this line was our spring constant.
Next, we constructed an apparatus to allow us to test at what velocity the steel ball left the crossbow. We then recorded a video with a scale reference and frame to track the change in position over time and find velocity. Our tracking was done through the Logger Pro software.
We can now compare the results to what we should have seen based on our calculations to determine if our calculations accurately model the system. We know from the law of conservation of energy that the initial energy should be equaling to final energy. We also know from the initial and final state of the systems that the only energy initially in the system is the potential energy from the springs, and the only energy at the end is the kinetic energy at the velocity of the ball. We can algebraically make an equation for velocity based on these facts. Based on our calculations for k and our own known delta and mass, we find the final velocity should be around 8.84 meters. Based on our Logger Pro data analysis, the actual release velocity was around 3.5 meters per second, meaning we have a percent error of about 60%. This is well outside the acceptable range, and we can conclude from here that a substantial amount of energy is being lost in our system. We expect there are two main sources of this loss: the kinetic friction between the wheels and the ground, and the poor design of the release mechanism. Ball bearings are only considered frictionless when under a sufficiently large load. We expect the weight of the cart to be inadequate for this, and ultimately lead to more sliding than rotation of the bearings. To minimize this in future experiments, we could have degreased the bearings to lower the rolling resistance, or add more release to the release mechanism. This also would have solved other issues within our system. The second issue we're experiencing was that the cart ended up having some final velocity once the ball was released. If we had also calculated for this velocity alongside the velocity of the ball, we may have gotten more reliable data and a value more close to our final result.